Okay,
So,
you're ready to go. Have a good session.
you,
Thank you for
how
introduction.
you can start, handling. Yeah, I just want to introduce the paper. Yeah, so hi everyone and welcome to the session multi-party computation number. And we start with, for this session, we start with the presentation of Han Liu on the paper pushing the limits of variance circuits, simpler, tighter, and more compact. So Han Liu, you can start.
Thanks for introduction. Hello everyone, I'm Han Liu from Shanghai Zhejiang University. Today I'm presenting a high-level overview of our paper about universal circuits. For any circuit C of size up to n, we can efficiently encode C with configuration string PC, such that the universal circuit configured under PC is functional equivalent to the original circuit C. And the universal circuits can be seen as a graph object called H-universal graphs, EUG in short. Before our work, the best size official EUG has size 4.5 n-log, and it is known to be lower bound by 3.64 n-log in Venus framework. In this work, we give a EUG construction of size 3 n-log, and we also lower bound the size of our EUG by 2.95 n-log under our framework. Notice that the size of our EUG is even smaller than the lower boundary in Venus framework, which is not a contradiction because our construction is not under Venus framework. MPC can preserve input privacy. In some situations, we may want to preserve functional privacy. Universal circuits can transform algorithm C into the configuration string PC. Then we invoke MPC for secure computation. While the privacy of algorithm C is preserved, we review some other application in our paper. A circuit is a DAG on the left hand, and a UC is an EUG on the right hand. Then a universal circuit simulates a circuit reduces to an EUG. Reduces to EUG edge embodies the corresponding DAG. Venus give a recursive EUG construction. Reduces the problem of constructing EUG to itself, but with much smaller size. This is achieved with a larger graph object called KV Suplo, SNK in short. As a first step, we give our intermediate construction that is a functional equivalence to Venus construction. It has roughly same size as Venus construction without any improvement. Further, there are some issues such as our intermediate construction has cycles. In other words, the graph of we construct is not even a DAG, not to mention an EUG. In our end construction, we remove these cycles, which brings additional benefits. Our end construction of much smaller size. We give an example to show how to remove the cycle. Node A matters. Node A matters is the previous node of node A in the smaller EUG. Then we delete edge number 1 and edge number 2 and add a new edge from the node A matters to the corresponding EUG. And node A plus is the next node of the node A in the smaller EUG. Then we delete edge number 3 and edge number 4 and add a new edge from the corresponding EUG to the node A plus. So the node A can be removed since the degree of node A is 0. Therefore, we can get a more compact EUG construction without affecting the functional of universal edge embeddings. This summarizes the size of our EUG and UC. The advantage of our construction over Sylvanus one is minus k, highlighted in red. Moreover, we prove the lower bound of 2.95 n log n for our construction. And we get a EUG construction of size 3 n log n, which is very close to the lower bound 2.95 n log n. Finally, we visualize the comparison with the previous works. Our construction improves over the best previous works by about 33%. The related works about universal circuits. That's all. Thank you.
Thank you, Lahanin Liu. Do anyone have questions for the presenter? So I have a small questions. So in the experiments, in the performance, you show the graph, and which kind of circuits do you use in your performance evaluations?
So I don't know.
So you have the input size of the circuit, right? And this is how you make. No.
I cannot hear.
So the next slide.
This one.
Yeah. So which kind of circuit do you use in the performance evaluations? Because you
this is I can help to answer also cause this work. So a universal circuit simulates an arbitrary circuit of size up to n. So then n is measured as the So if you want to simulate an arbitrary circuit of size n, then the size of EUG is like all universal circuit is measured in terms of the function of this n. So we use this circuit size of the UC as a function of n. As you can see, the previous works, so we need like n 4.75 n log n, or recently improved to 4.5 n log n. And in this work, we reduce by like 33% and reduce it to 3 n log n. And we also prove a lower bound.
Works. Yeah, thank you. Yeah, so thank you for your question, your answers. Yeah, I think the reason, like, because I see that you say the input size n and n from 1,000 from 100 to the 10, 8. So you generate the circuit like the simulate. You just generate the circuit, right? Right. The circuit is random. It's not like AES or SHA-1.
And it's just a random circuit.
Yeah. Thank you. Yeah. Thank you. Yeah, nice work. Any other questions? Oh yeah, so thank you, Han Liu.
Thank you.
Let me move to the next presentation. So the next talk here is for Gayatri Girimela will present the work on oblivious key value stores and implication for private set intersections. Yeah.
Thank you, Ni, for the introduction. So this is joint work with Benny Pincus, Mike Roslick, Ni Trio, and Avishai Yanai. So thank you, and let's get started. In private set intersection, Alice and Bob each have as input a private set of items. And they want to run a two-party protocol so that Bob, who learns the output, learns the intersection of both the sets. Here, he learns the items they have in common and nothing else about Alice's set. A common scenario that we see in a host of PSI protocols is Alice has a function f that she wants to convey to Bob. For most key values, Alice doesn't care what this function evaluates to. For a few special keys, K star, she wants to convey specially crafted random values to Bob. This small set of keys K star depend on Alice's input, so she wishes to hide it. So the goal is for Alice to compactly convey these key value pairs to Bob while hiding key star. In PSI and all the related protocols that we consider, the values associated with the keys or the special keys are usually uniformly random. So they end up using the technique of polynomials to convey their key value pairs. That is, they interpolate a polynomial so that when you evaluate it on any of the keys that you require, you learn the correct associated value. Since the values are uniformly random, the interpolated polynomial also looks uniformly random. So it effectively hides the input or the special keys. And we see polynomials used like this in the papers that I've listed. So in our work, we abstract the specific properties that we require from polynomials in our application and define the notion of oblivious key value stores as data structures where you can encode n key value pairs into an object S, and later you can decode using a decode algorithm and any key of your choice to learn the right associated value. You can also decode in any key that lies outside the set, and you end up learning some value that you don't care about. So this is a key value store, and it becomes oblivious when the object S effectively hides all the encoded keys. For OKVS, we measure the efficiency of it in terms of, one is the size of the OKVS. So let's assume that there are M field elements in the OKVS. We want this M to be as close to N as possible. Also, we're interested in having very efficient encoding time, ideally linear in this number of keys, key value pairs that we're encoding, and we want efficient decoding time. And if our OKVS is a randomized construction, then there's also an associated failure probability that we need to consider. So in our work, we study the general notion of oblivious key value stores and catalog all existing constructions and compare them in terms of their various efficiencies, including polynomials. Then, in the PSI context, we look at the PRTY20 paper, which uses a data structure called Paxos to obtain a very efficient, malicious, secure two-party PSI protocol. We observe that Paxos can be categorized as an OKVS that relies on the analysis of cuckoo hashing with two hash functions. Again, this construction is randomized, and we need to ensure that it encodes correctly the n key value pairs, except with negligible failure probability. In Paxos, they show an asymptotic analysis of whether the failure probability. But it remains highly non-trivial to translate this asymptotic analysis into actual concrete parameters used to instantiate an instance of PSI. Therefore, when they implement, they rely on some heuristics to determine the various concrete parameters needed. Our goal is to obtain a better OKVS. We know that we can use cuckoo hashing with an analysis with 3 hash functions to obtain better efficiency in terms of the size of the OKVS. Better size would immediately imply better communication performance in the PSI. So our first task is that, our first construction is that we extrapolate the concrete parameters from the Paxos data structure, and we show how to obtain an OKVS using cuckoo hashing with 3 hash functions. But again, we're not satisfied with how we obtain the concrete parameters. We want some more empirical confidence. And to run experiments to verify failure probability of the order of 2 to the minus 40 is extremely resource intensive. You have to invest millions of core hours, and still it wouldn't be enough. And suppose you need an OKVS for an application that needs, say, 2 to the minus 80 failure probability, then it's certainly not feasible to empirically verify it. So we observe that if the failure probability was more reasonable, like say 2 to the minus 15, then we can verify something like this easily, even on our personal laptops, and achieve very high statistical confidence. So we present techniques where for some constant C, we can compose a set of weaker OKVS with failure probability P to obtain a stronger OKVS with failure probability P to the C, while ensuring that there's minimal overhead in terms of the size of the OKVS. Thus, we can we can instantiate our OKVS with cuckoo hashing with 3 hash functions and set the concrete parameters with empirical confidence. Our better OKVS gives us the fastest malicious two-party PSI protocol and many applications. I'll very quickly summarize our applications. Our OKVS can replace any random encoding task, including the use of polynomials in the following applications. In the use, especially the first one is in sparse OT extension, which was used to get a communication efficient PSI in the semi-honest setting. It can also be used to replace the use of polynomials in an oblivious programmable PRF, which is used to build circuit PSI. A version of it is used to obtain private set union. And it's also a major building block in multi-party PSI. Apart from using OKVS as a plugin replacement, we also see that one of the multi-party PSI protocols presented in KMPRT 17 actually turns out to be a malicious secure. And we show a qualitative analysis of how this is the most efficient malicious secure multi-party PSI to date. And as a flagship example, we consider the OT Paxos-based PSI protocol in PRTY 20 and replace it with our more efficient OKVS to obtain the fastest malicious two-party PSI, which is now empirically verified. We also show a generalization and convert this PSI protocol into a vector OLE and OKVS PSI protocol. And you have to look at the paper to, I invite you to look at the paper to know what a linear OKVS is. And as a concurrent work, there's a vector OLE and Paxos-based PSI that is presented by RS21. And we suggest that you can replace their Paxos also with our better OKVS for better performance. So I'll end with that. Thank you so much for listening.
Thank you, Yatri, for the nice talk. Do we have a question from audience? Oh, is it actually also my work? So
yeah,
I know it works. Okay, so maybe we can, if we don't have any question from the chat or audience, so we can move to the next talk.
okay, thank you.
So
the next talk will be PC from HE. Oh yeah, sorry. The next talk will be HM2K MPC from HE over Z2 to the K with the new things, simpler reshares and better CKP. And he.
Okay, thank you for the introduction. And I will present our work named megahertz 2K MPC from HE over Z2K messages. This is a joint work with my advisor, Johnny Chan, and Dr. Dongwoo Kim of Western Digital. So our work, megahertz 2K, belongs to so-called speeds family, which follows the approach of speeds to construct an MPC protocol secure against actively corrupted majority. All these protocols leverage high parallelism of lattice-based homomorphic encryption in pre-processing phase to securely and efficiently generate authenticated reverse triples. Meanwhile, all these works are protocols for arithmetic circuits over large prime field ZP. More recent work named Speeds 2K highlights that the importance of MPC over Z2K as they are more suitable for modern CPUs. Speeds 2K mainly follows the approach of speeds, but they are based on oblivious transfer rather than homomorphic encryption. And the authors of Speeds 2K raised the question of, can we construct an efficient HE-based MPC over Z2K, because known techniques for a ZP case do not seem to generalize well to the case of Z2K. So our question was, how can we make the best use of homomorphic encryption for MPC over Z2K in Speed's framework? In more details, we have two major complications here. First, conventional HE packing method for ZP messages, which provides high parallelism through this ring isomorphism, does not work with Z2K messages. So this means that we need new packing methods for Z2K with nice packing density. Second, when we leverage the lattice-based homomorphic encryption, we usually choose power of 2 cyclotomic polynomials because they have nice structures and nice properties. However, power of 2 cyclotomic polynomials are irreducible modulo 2 to the k. And this means that we cannot leverage CRT parallelism for Z2 packings. And this forbids us from using power of 2 cyclotomic polynomials for Z2K messages. Accordingly, we cannot use known techniques which leverage the structure of power of 2 cyclotomic polynomials. This includes the work by Behamuda et al. On better ZKP for lattice encryptions. So in short, our contribution is a new MPC protocol over Z2K, secure against actively corrupted majority, which offers a substantial improvements in amortized communication cost and memory consumption versus previous best results. And as our title suggests, these improvements are based on 3 independent technical contributions. First is that we propose a new packing method for Z2K messages, which offers a nice packing density of roughly a half. The interesting part is that our packing method is based on what we call tweaked interpolation over Z2K. Note that conventional interpolation cannot be applied here because in general, over rings, we cannot, the interpolation is impossible due to the existence of 0 divisors. And second, simpler reshare. Reshare protocol is one of the main components of Speed's protocol. And somehow it is affected by the structure of our new packing method, namely by the level dependency of the packings. Reshare protocol so we proposed a new reshare protocol for level dependent packings, which is inevitable feature for packing methods for Z2K messages. And this closed the gap between ZP case and Z2K case caused by this level dependency. And for last, we designed a better ZKP, which by enlarging the challenge space in Schnorr-like ZKP over ZX quotiented by cyclotomic polynomial of prime P. This offers these benefits in both in amortized communication cost and memory consumption. And this improvement is based on a non-trivial extension of mathematical lemma in Behamuda et al.'s work, which is about coefficient size of inverses in ZX quotiented by this power of 2 cyclotomic polynomials. And yes, this is it. And thank you for listening.
Thank you for the night talk. Do we have any question from audience? A hand in the chat. Yeah, I think let's wait. Okay, yeah, I think, yeah, thank you, Q, again for the presentations. So let we move to the next talk.
Yeah.
Okay, yeah, so the next talk will be, can you, okay, yeah.
Yeah, okay.
So the next talk will be Sabina GMW style compiler for MPC with preprocessing, and Ariel will give a talk.
Yes, thank you. So this is a joint work with Alette Boyle, Niv Gilboa, and Yuvali Shai. Right, so, okay, so in this talk, we consider multi-party computation in the pre-processing model. In this model, the execution is divided into two phases, an online phase or the pre-processing phase and an online phase, an offline phase and an online phase. The goal of the offline phase is to produce correlated randomness, which is later used by the parties in the online execution to compute the desired functionality over their private inputs. Now, another way to look at this model is to view this execution as an execution with a trusted dealer who gives the parties correlated randomness and then later design a secure protocol to distribute the dealer. Now, this model is in particular useful in the dishonest majority setting, which we consider in this work. In this challenging setting where no one trusts no one, we know that achieving secure multi-party computation requires using expensive tools with high communication or tools that are computationally expensive. However, in this model, we can move all the expensive machinery into the offline phase and obtain an online execution which is fast, cheap, and information theoretic. And now in this work, we mainly focus on the online execution and its efficiency, and we look at two main metrics, the online communication cost and the amount of correlated randomness given by the trusted dealer. Now, the standard approach for computing MPC in the preprocessing model is to use Beaver triple. And here the dealer gives the parties shares of random multiplication triples, and these are used to multiply shared values in the online execution. And in this table, you can see the exact communication cost, the exact amount of correlated randomness per multiplication. And as you can see, there are two variants for this approach with circuit-independent preprocessing and with circuit-dependent preprocessing. When we allow circuit-dependent preprocessing, this means that the dealer knows the structure of the circuit, and this can be used to reduce the cost slightly. And also, we can use PRG-based compression, and then we can give each party one seed from which it derives all these shares. But even with this optimization, we still need to give one element per gate to a single party because one share of A times B is fixed and not random. Now, these are the costs to achieve semi-honest security. To achieve malicious security, so the most popular approach currently is the speed approach, where the dealer gives also, for each multiplication gate, he gives also an authenticated version of each random triple by multiplying each value in each triple with a random global mask. Now, the main advantage of this approach is that the online communication cost with malicious security remains the same as the communication cost with semi-honest security. But of course, the amount of correlated randomness grows. For large fields, it grows by a factor of 2, and for small fields, it grows by a factor of kappa, where kappa is the statistical security parameter, because the authenticated triple needs to be generated over an extension field with size that depends on the statistical parameter. Now, another approach, which was first introduced in the Minimac protocol for small fields, allows achieving constant correlated randomness overhead, which does not depend on the statistical security parameter. However, this comes at the expense of increasing the online communication cost. So now the communication cost with malicious security is higher than the cost with semi-honest security. So as can be seen from this slide, there is currently a trade-off between the communication overhead and the correlated randomness overhead. And this raises the following question. Can we achieve malicious security where both the amortized online communication cost and the amortized correlated randomness are the same as for semi-honest security, and of course, without introducing any new assumption? And in this work, we give a positive answer to this question. And in particular, our main result is the following. So given an arithmetic circuit C, which is defined over some finite field or over the ring of integers modulo 2 to the k, then we can take every natural semi-honest MPC protocol which computes C, and I will explain what natural means in the next slide, and compile it into malicious security where both the additional correlated randomness and the additional communication are logarithmic in the size of the circuit times some statistical parameter, which means that amortized over the circuit, the cost per multiplication gate, per single multiplication gate, remain the same as the cost with semi-honest security. Right, so the high-level framework of our solution is the following. So first, the parties additively share their inputs, then they run a semi-honest protocol to compute the circuit. And here, addition gates can be locally computed, but the parties need to interact to compute multiplication gates. And therefore, they need to verify that all multiplication gates were computed correctly. And our main contribution is a new verification protocol to verify the correctness of all multiplications with logarithmic amount of communication and logarithmic amount of correlated randomness. If this step ends successfully, then the parties proceed to reveal the outputs. So the main requirements from our semi-honest protocol are, we have two requirements. So first, that the protocol is additively secure, meaning that the adversary can only add errors to the wires. And the second property is what we call star sharing compliance, which basically means that each secret can be reconstructed by each party and the dealer. And fortunately, many secret sharing-based semi-honest protocols, including Beaver-style protocols, satisfy these properties and therefore can be used as the underlying semi-honest protocol in our framework. So let me say just a few words about our verification protocol. So at a very high level, the goal is to verify that if we take a random linear combination of all the outputs of all multiplication gates minus the multiplication of the inputs, and these values are shared across the parties, then the result will be 0. So if we denote this one value that we want to check equality to 0 by V, then the main idea of our verification protocol is that first the parties can locally compute an additive sharing of V, but of course they cannot simply open it because the malicious parties can open to any value they want. So we first convert the additive sharing into a robust secret sharing by letting each party secret share its additive share in a robust way by sharing it such that they generate a 2 out of 2 additive sharing between each party and the dealer, which means that an honest party and the dealer can reconstruct the secret. Now, of course, then we have a robust secret sharing of V, and then we can open it and check equality to 0. But of course, this is not enough because a malicious party can also secret share an incorrect value. So we have another step where each party proves that it shared the correct VI. And here we use a tool which is called distributed zero-knowledge proof due to Bonet et al. From Crypto 19 to prove that each party shared the correct value. And with this tool, a prover can prove the correctness of some statement over an input that is shared across several verifiers. And Bonet et al. Showed that if the statement to be proven is a degree 2 polynomial, and the input is robustly shared across the verifiers, which means that the shares held by the honest parties alone are enough to reconstruct the secret, then we can have a proof with the logarithmic amount of communication and with soundness that holds even if a malicious prover colludes with a subset of the verifiers. This tool is very useful to achieve malicious security in MPC because many computations in MPC are indeed degree 2 computations. And this tool was used before to achieve malicious security and even full security in the honest majority setting, relying on the fact that the secret sharing in the honest majority setting is inherently robust. But when we move to the dishonest majority setting in our work, so first, indeed, the computations are still degree 2 polynomials. So this is good, but the main challenge is how to achieve robustness, how to maintain robustness throughout the zero-knowledge proof execution. And of course, without increasing the amount of correlated randomness. So the main technical idea that we have is to use the dealer to achieve robustness. And we show how throughout the verification protocol, we maintain the invariant where each piece of information is 2 out of 2 additively shared between each party and the dealer. So again, we have the property that an honest party and the dealer can reconstruct basically everything. And we do it by using the dealer as one of the verifiers in the zero-knowledge proof. And now, since the amount of communication in the zero-knowledge proof is logarithmic, this means that also the amount of communication from the side of the dealer is also logarithmic in the original circuit's size. And then we show how the dealer can pre-compute all his messages in the zero-knowledge proof, and give it as correlated randomness. And this is how we achieve our result, that eventually the amount of correlated randomness given by the dealer in the verification step is logarithmic in the size of the circuit. And with this, I will end my talk. Thank you very much.
Thank you, Ariel. Question from audience. Yeah, so if so, like, thank you, Ariel, for the presentation. And we can move to the next. So the next talk will be limits on adaptive security of Yao garbling, and Karim will give a talk.
Yes. So let me share the screens. Can you see it now? Yes.
Yeah, I see it.
Okay, so my name is Karin Klein, and this talk will be on limits on the adaptive security of Yao's garbling. It is joint work with Chetan Kamat, Krzysztof Gieczak, and Daniel Wicks. Consider the following scenario. Alice holds some circuit C, Bob some input X, and they want to jointly evaluate the circuit on the input without revealing their respective secret information. And to this aim, Yao suggested the following solution. So first, Alice can garble the circuit, send over the garbled circuit C tilde to Bob. And then Alice and Bob run an oblivious transfer protocol so that Bob learns exactly the garbling of his input. Bob can then evaluate the garbled circuit on the garbled input to learn the output C of X. And while Yao suggested this solution already in the 80s, it was only much later that the security of Yao's garbling scheme was formally analyzed. The first formal security proof was due to Lindell and Pincus in 2009. However, they only proved security in a selective model, where the input is known ahead of time. But in practice, we would like to compute the garbling of the circuit in an offline preprocessing phase, so we would require adaptive security. There exists a trivial reduction that proves adaptive security based on the selective security on a scheme by simply randomly guessing the input. However, unfortunately, this leads to a loss in security that is exponential in the input length. The first non-trivial adaptive security proof was due to Ciofagoli and Wicks, who managed to improve this loss factor to be exponential only in the depth of the circuit. So for NC1 circuits, they obtain polynomial loss in security. In our paper, we are now interested in lower bounds on this loss in security. Namely, we prove that for any black box proof of adaptive indistinguishability for Yao's garbling scheme for circuits with n-bit input, 1-bit output, the FD, from an in-CPA secure secret key encryption scheme, the security loss involved will be exponential in square root of d. And I want to make 2 remarks on this result. The first one is that our lower bound only applies to Yao's specific construction. So note that we do not prove a separation of garbled circuits from one-way functions. And in fact, there exists a scheme due to Hemingway et al. That is adaptively secure based only on one-way functions. And what they are using to achieve this is somewhere equivocal encryption. However, this scheme is less efficient than Yao's original construction, since the online complexity increases with the pebble complexity of the circuit. As a second remark, I want to highlight that our lower bounds hold even for indistinguishability, which is a weaker notion than the usually considered simulatability notion for garbled circuits. However, since we're considering lower bounds, this only strengthens our results. Furthermore, I was cheating a bit on the previous slide, namely Ciofagoli and Wicks do not prove adaptive security of the original scheme by Yao, but a slight modification where the output mapping is sent in the online phase instead of the offline phase. So for our lower bound, we also consider this variant of Yao, and again, this only makes our results stronger. The only previously known limitation to Yao's scheme was due to Applebaum et al., who proved that Yao's original scheme, so where the output mapping is sent in the offline phase, is not adaptively simulatable. And for this result, they used circuits with large output. So our lower bound differs in 3 aspects. First, we consider a weaker security notion. Second, we consider a scheme to which the lower bound by Applebaum et al. Does not apply. And finally, we consider circuits with constant output. On the other hand, we require large depth, whereas the result by Applebaum et al. Holds for small depth. To achieve our results, we define 2 oracles F and A, where F is an ideal secret key encryption scheme. So in particular, it is information theoretically in CCA secure. And A is an inefficient adversary that breaks Yao's scheme by simply brute force breaking the underlying encryption scheme. But still, it is not too helpful for any reduction that aims to break this encryption scheme. And the main idea here is inspired by Jafagoli and Wicks, who obtained their upper bound via some pebbling game on graphs. We, in contrast, use lower bounds for some appropriate pebbling game to establish our lower bounds for security. And while this idea is rather simple, it turned out quite tricky to realize it. Namely, the main issues were to design a suitable circuit C with constant output, and to relate a garbled circuit input pair to a pebbling configuration. But with this, I want to conclude this brief overview of our work and want to refer to the longer version of my talk for more details, and especially to the full version of our paper for precise proofs. Thank you for your attention. I'm happy to answer any questions if there are.
Thank you for the nice presentations. Let me check if they have any question from audience. We still have 8 minutes left for the sessions. If any question related to previous presentation in this, you can ask me.
I stop sharing, right?
Yeah. Okay, cool. So thank you. So I think they have maybe too early mornings. So yeah, so maybe I think we can have like the next sessions. Right? Can you stop the video recording?